Hello everyone. So in today's lecture we will see relation between beta and gamma functions. In the previous lectures we have already seen the properties of beta function and gamma function. So now we will see the relation between beta and gamma functions. So relation between beta and gamma function is equivalent to beta m comma n is equivalent to gamma of n m into gamma of n divided by the denominator part gamma m plus n, and where m is greater than 0 and n is also greater than 0. So we have to prove that what is the relation between beta and gamma function. So we will prove this formula. We will prove this relationship. Okay. So proof. This can be asked in your exam that prove the relation between beta and gamma functions. So during that time you have to show the proof. Okay. So for that, first of all, by the definition of gamma function, which we have seen in the previous lectures. So by definition of gamma functions, we can write that gamma n is equivalent to integration of 0 to infinite e raised to minus x raised to n minus 1 dx. Okay, and from this equation we can also write that gamma n is equivalent to z raised to n 0 to infinity e raised to minus zx x raised to n minus 1 dx. So this is our equation 1 and this is our equation 2. But how we got equation 2? If you put x equal to zy in equation 1, if you substitute this value in this equation, then you will get this equation. But no need to prove that, no need to put the value, and you can try it, but in proof you don't have to show it. So you can directly write this equation, but you get equation 2 by putting x equal to zy in equation 1. So you directly have to remember this both the equations. Okay, so now from equation 2 we can write that n divided by z raised to n is equivalent to 0 to infinity e raised to minus zx x raised to n minus 1 dx. Okay, so this is our equation 3. But you always have to remember that here there is z. Okay, so this z will always be, this z should always be present in the denominator part here, and this n you have to write here n z raised to n, and you have to write here gamma n. This will be useful to you in the further when we will solve the examples, because whenever this type of equation will be given, you can from this equation, from this integral, you can directly write this term. How you can write it? You have to write this z term, you have to write this e raised to term in the denominator part, and x raised to term and you have to write here z raised to n in the, and the numerator part you have to write gamma n. Okay, this n will be in the here and this z will be here. This expression we will use in the further equations. Okay, but you have to remember that whenever you are given like this, you can directly write like this from this z and n. Here there can be anything that will be represented in this form. Okay, so now we will multiply equation 3 both the side by, we'll multiply this equation 3 both the side by z raised to m minus 1 and e raised to minus z, and then we will integrate it, and then integrate with respect to z from z equal to 0 to z tends to infinity. This is our limit. Okay, so we will multiply this equation both the side by z raised to m minus 1 and e raised to minus z. So we can rewrite this equation as gamma n 0 to infinity e raised to minus z, z raised to m minus 1 dz, and this zn we will take here. Okay, so that is equivalent to 0 to infinity e raised to minus z, z raised to m minus 1 whole bracket, the zn will come here, so zn, and this term will remain as it is because you just have to multiply by this term. Okay, 0 to infinity e raised to minus zx x raised to n minus 1 dx. Okay, we just multiplied it by this term on both the side. Everything other than this terms will remain as it is. So now from this equation we can write, from equation 1, what is our equation 1? That e raised to minus x, x raised to n minus 1 can be written as gamma of n. Here similarly we have e raised to minus z, z raised to m minus 1. So that can be written as gamma m. Okay, so we will write it from equation 1. We can write gamma n, and this whole term we can write as gamma m equal to 0 to infinity. We will take this limit outside, so we will get e raised to minus z 1 plus x. This e raised to minus z and this is e raised to minus z, we multiplied it, and similarly we will multiply z term, so we will get z raised to m plus n minus 1, x raised to n minus 1 will remain as it is, and dx into dz. Okay, so now if we change the order of this equation, then we get, now changing the order of integration, we will change the order of equation. Okay, order of integration, sorry. So we can write gamma n gamma m equal to 0 to infinity x raised to n minus 1, and here we will write 0 to infinity e raised to minus z 1 plus x z raised to m plus n minus 1 dz. So this is our dz term, and this term will be dx term that we will write outside. Okay, so we have just changed the order of integration. So now from equation 3 we can write, so what was our equation 3? This is our equation 3. Okay, so I told you that this equation will be useful in the further proof. So from this we can directly write this term. Okay, you can see that this whole integral term is equivalent to this whole integral term. Okay, and whenever we get such type of term, we can directly write in this form. Okay, so how we will write this term in this form, that we will write it. Okay, that is n gamma m is equivalent to 0 to infinity. This term will remain as it is. We have to just change this term. So what I said, that this n is there, that you have to write here and here. So what is our n here? This is our n. n minus 1. So this is our n minus 1. So you have to write this in the numerator part as gamma n, because here it is gamma n, upon n whatever is with x you have to write in the denominator part. Whatever is present is with the z, you have to write in the denominator part. So here we have 1 plus x. Okay, so 1 plus x will be in the denominator part, and again raised to n. So what is our n? N is m plus n. So here we can write that our n is equal to m plus n, and the z is equivalent to 1 plus x. So we substituted in this equation. Okay, equation 3. Okay, and this term will remain as it is. Sorry. Okay, we have converted this, and we have converted this term into this term. So dx. This conversion is over. So we have converted this big term into very small term, and now we can easily prove it. So we will continue it. Now we will prove. Now we can write this n gamma m, and this m gamma m plus n we can write here in the denominator part. So we get m plus n. This we took here. Okay, and here we have 0 to infinity x raised to n minus 1 upon 1 plus x raised to m plus n dx. Okay, but in the further lectures we proved that this term is equivalent to beta m comma n. Okay, and further in the previous lectures we have proved this, that this term is equivalent to this. So we can write that here in place of this term, here in place of this whole term we can write beta m comma n. Okay, because we have proved this, that this term is equivalent to beta m comma n. So we can write here that gamma m divided by gamma m plus n is equivalent to beta m comma n, and that is what we have to prove. Okay, so we got the answer, we proved it, so we can write it hence proved. So this is the relation between beta and gamma functions. Okay, so now we will prove that gamma 1 by 2 is equivalent to under root pi. This is also asked in exams, that you have to prove that gamma 1 by 2 is equivalent to under root pi. Then how you will prove it? It is very easy. So we will prove it. Okay, so proof. We know that property of beta m comma n, that is beta m comma n, is equivalent to gamma m into gamma n upon gamma m plus n. Just we proved in we have proved the relation, okay, between beta and gamma. So that we are writing. So this is our equation 1. And also we know one property of beta function, that is also by property of beta function. We know this property, that beta m comma n is equivalent to 0 to pi by 2 sine theta raised to 2m minus 1 and cos theta raised to 2n minus 1 d theta. So we will consider this as equation 2. Okay, now from 1 and 2, that is from equation 1 and 2, we can write that this is our beta m comma n. So we can substitute this whole value here. in the equation 1. So we'll substitute it. So from 1 and 2 we can write that 2, 0, 2 pi by 2. In place of beta m comma n, we will write this equation in equation 1. Okay, so sine theta raised to 2m minus 1 cos theta raised to 2n minus 1 d theta, and this term will remain as it is, that is gamma m into gamma n divided by gamma m plus n. We have just substituted this value of beta m comma n here in equation 1. Okay, now as we have to prove that gamma 1 by 2 is equivalent to under root pi, we will put m equal to 1 by 2. We will put m equal to 1 by 2 in this equation, and also n equal to 1 by 2. So whenever we will put m equal to 1 by 2, we can write that 2m minus 1 is equivalent to 0, and here also we can write 2n minus 1 is equivalent to 0. Okay, so now we will put this value in this equation, that is equation number 3. Then we get 2, 0 to pi by 2 sine theta raised to 2, m is 1 by 2 minus 1 cos theta 2 raised to 1 by 2 minus 1 d theta, that is equal to gamma m gamma n divided by gamma m plus n. Now this 2 and 2 get cancelled, and sine theta 1 minus 1, that is 0. So we can write it as 2 integral 0 to pi by 2 sine theta raised to 0 cos theta raised to 0 d theta, that is equivalent to m gamma n divided by gamma m plus n. Okay, now anything raised to 0 is 1. So here we will get 1, and here also we will get 1. So we can write it as 2, 0 to pi by 2 1 into 1 d theta, that is equivalent to, from this equation we are writing, okay, gamma m gamma n divided by m plus n. Okay, now differentiation of 1 d theta is theta. So 2 theta, and then we put limit here 0 to pi by 2 gamma m gamma n. Here also we will substitute the value of m and n. Here we took m equal to 1 by 2 and n equal to 1 by 2. So we can write here also 1 by 2 gamma 1 by 2 divided by gamma 1 by 2 plus 1 by 2. Okay. Now if we put limit here, then we get 2 pi by 2 minus 0. So 2 pi by 2, and this will be gamma 1 by 2. You can write it gamma 1 by 2 whole square, and 1 by 2 plus 1 by 2 is 1. So here we will get 1. Now this 2 and 2 get cancelled, so we get pi. And we have proved in the previous lectures that value of gamma 1 is 1. Okay, so we will get gamma 1 by 2 whole square divided by this 1. So we can write this square will go here, so we will get under root pi equal to gamma 1 by 2. So hence we proved that gamma 1 by 2 is equivalent to pi. We have to prove it, and we have proved it. Okay, so this is our proof. So we can write it as hence proved. Okay. So now we will solve an example. Evaluate beta in the bracket 9 by 2 and 7 by 2 is given. Okay, So whenever you are given this type of example to solve, then you just have to write, first of all you have to write the property of beta m comma n, that is beta m comma n is equivalent to 2, 0 to pi by 2 sine 2 raised to sine raised to 2m minus 1 theta and cos 2n minus 1 theta d theta. We have already proved this property in the previous lectures, so you directly have to write this property here. Now uh, here we can say that this is the form of beta m comma n. So our m will be 9 by 2 and n will be 7 by 2. So here we will substitute m equal to 9 by 2 and n equal to 7 by 2 in equation 1. This is our equation 1. Okay, so we will get 2 integral 0 to pi by 2 sine raised to 2 into 9 by 2 minus 1 theta into cos 2 into 7 by 2 minus 1 theta into d theta. This 2 and 2 will get cancelled, so we will get 9 minus 1, that is 8, and here we will get 7 minus 1, that is 6. So 2 integral 0 to pi by 2 sine raised to 8 theta into cos raised to 6 theta d theta. Okay, but you have to remember this property that 0 to pi by 2 sine raised to m theta into cos raised to n theta d theta is always equivalent to m plus 1 by 2 gamma m plus 1 by 2 into gamma n plus 1 by 2 divided by gamma m plus n plus 2 divided by 2. Okay, this is the property. This is one formula that you have to remember, that whenever you get this form, that is sine raised to m theta and cos raised to n theta, then you directly have to substitute value of m and n here in this equation. So if we directly substitute value, then we get beta 9 by 2 comma 7 by 2 equal to, from this equation, that is from equation 2, we can say that our m is 8. According to this equation, our m is 8 and n is 6. So we directly have to put this value in this equation. So we will get, this 2 will remain as it is. 2, this our m is 8, so 8 plus 1 by 2 and 6 plus 1 by 2 divided by this m plus n plus 2 divided by 2. Sorry, in the formula here there is 2. Okay, so here also we will get 2. So 8 plus 6 plus 2 by 2, that is equivalent to, this 2 and 2 will get cancelled. 8 plus 1 is 9 by 2 and 7 by 2 divided by, this is 16 by 2. Okay, so that is equivalent to 8. This will get cancelled, so we will get 9 by 2, gamma 9 by 2, gamma 7 by 2 divided by gamma 8. Okay, so further how we will solve the equation, then we can solve this equation as, 1 minute, how we will solve it. You just have to subtract 1 from this equation till you get 1 by 2. So 9 by 2 minus 1 is 7 by 2. So you have to write here 7 by 2. Again 7 by 2 minus 1 is equal to 5 by 2. So again you have to write 5 by 2. Again 5 by 2 minus 1 is equivalent to 3 by 2. You have to subtract 1 and you have to multiply each term. Okay, again 3 by 2 minus 1, that is equal to 1 by 2, and after 1 by 2 you have to write under root pi, because we have just proved that gamma 1 by 2 was equivalent to under root pi. So you have to write it that after you reach 1 by 2 you have to write under root pi. Okay, so 9 by 2 solution is over. Now you have to go for 7 by 2. So for 7 by 2 you will write 7 by 2 minus 1, that is 5 by 2. Again 5 by 2 minus 1, that is 3 by 2. 3 by 2 minus 1 is 1 by 2. Again after 1 by 2 you have to write pi. After 1 by you reach 1 by 2, you always have to write under root pi. Okay, divided by, here we have 8, but we know that gamma n plus 1 is always equal to n factorial. So here if we have 8, then we can write that 7 plus 1 is equal to 7 factorial. So we can write here 7 factorial. Okay, so we will write it as 7 factorial. Now solving this, we get 7 into 5 into 3 into 1. This root pi and this root pi, we can write it as pi. Again 5 into 3 into 1 divide by 2, and that is how many 2 are there? 1 2 3 4 5 6 7. Okay, so you have to write 2 raised to 7 divided by 7 factorial. So I can rewrite this equation as 7 into 5 into, I'm writing this pi outside. Okay, this pi I'm writing outside. So 5 into 3 into 1 into again 5 into 3 into 1 divided by 2 raised to 7 into 7 factorial. But 7 factorial is equivalent to 7 into 6 into 5 into 4 into 3 into 2 into 1. Okay, so from this we will, this 7 and this 7 will get cancelled, this 5 and this 5 will get cancelled, this 3 and this 3, 1 and 1. Okay, again, so what will remain? So here we will get, and this 3 will be cancelled out with this, so we will get 2 here. So and we can write this 4 as 2 into 2, so we will get here 2 raised to 7, then 8 9, and okay, this 2 will, we can write this equation as, here we only 5 is remaining, so 5 pi divided by this 2 raised to 7 is there, and again this 4 to our present, so we will add them here. So we can write 7 plus 4 is 11, so we get 5 pi divided by 2 raised to 11. So this is the answer of this question, that is beta 9 by 2 comma 7 by 2. And once again I am repeating, whenever you are getting 1 by 2 here, then only you have to write this under root pi. Okay, whenever you are decreasing, subtracting 1 and if you are getting 2, then you don't have to write this term. But if you are getting 1 by 2, then you have to, as we have proved that gamma 1 by 2 is equivalent to under root pi. So during that time, whenever you get 1 by 2, you have to write under root pi. Otherwise, you don't have to write it. Okay. So thank you everyone. I hope you all liked my video lecture. Thank you.